Now, in this section we are going to put all this understanding together about the molecular dynamics program and how we start with the initial position of crystal structure, and then we can use the same potential force or potential energy function, in this case Leonard-Jonesium type, and calculate all these three different phases. So, and we are going to now pay attention to the property calculation, because that is what we are doing, the property averaging and iteration of the time. So, this simulation we have seen it earlier in a different context, but now think as you are a programmer who is now calculating these trajectories and looking at the average properties and looking at different boundary conditions, applying some of the minimum image criteria, applying the things what we call as the periodic boundary condition or reflecting boundary condition, or even putting some pressure on the system. So, we are going to look at it for a few minutes, and then we will understand how this program is set up. So, this is a program which has 200 particles, and these are all same species of the particle, green particle, and then let us say they are argon particles, and then you are going to look at the particle type. So, here are the things that we are calculating: absolute kinetic energy, relative kinetic energy, potential energy, mass, trajectories, and we can also look at selected trajectories. Here are the options: we can graph update, update graph every step, now show spectrum. So, now you are looking at distribution of kinetic energy, relative kinetic energy, potential energy and mass. You are looking at show different magnifications. We are looking at select delay. You can add some more delay, short delay or medium delay, long delays, disable all notices. That's just, and in this case you can also select different number of time step, at which point we are going to spit out and show the property averages. Now, you understand that these are the averages. We have time, temperature, kinetic energy, potential energy, and density, volume and pressure. These were the things which we were looking at earlier as well. So, now let us look at that. We also have additional parameters, which is number density, which is the size of the box. As you change the volume of the box, you can change the number density, because number of particles over the volume, that gives you volume of the simulation box, that give you the number density. We can look at interaction parameters, which is fine. And also you can look at two boundary conditions: reflecting walls, periodic boundary condition, which is very important for the bulk property calculation. Then you have rigid container, or you have container with piston, and in that you can also lock the piston, or you do not have piston. We have seen this. So, now initial condition here is the crystalline structure. Now, let us start with that, and I will also put some real units here. So, you can see how it looks at the real units. Now, once we start here, now you have to let it equilibrate. So, now we are going to wait for, let us say these are the time step, and this time step in the real time they are showing femtosecond 0.009. So, let us say this is time in second 10 to the power minus 10, 1.8, 2.0, etc. is growing up, and temperature is almost constant to the third digit after decimal. Kinetic energy is constant up to the 4. Now, kinetic energy, there is no B particle. Potential energy is also becoming constant. So, we can say we have reached an equilibration stage. So, we pause it here. So, now once the equilibrium state has reached, now we are ready to calculate few other properties. Now, we are starting with the crystalline phase. So, let us look at that. Now, in this case, when we started, let us look at trajectories. So, here are the trajectories. You can see that they are almost at the same point. Let us look at some properties: temperature versus time, kinetic energy versus time, constant. Then number density is same, volume is same. So, we are looking at equilibrium. Velocity distribution is constant up to the 4 digits. Now, you are looking at velocity distribution for the particle B. Displacement of all particles, not much. This is the dist. So, this is mean square displacement that you are looking at. So, it is a constant property. Average square displacement versus time. So, if you look at not much of that, it's very, very small. So, now let us change the system. It has the heat bath. So, that is why temperature is constant. Let us say if we reduce the heat bath, what happens? Now, you are seeing that average displacement versus time is growing, because the system is now growing with it. So, now if I look at kinetic energy is fluctuating, and look at the volume pressure is fluctuating sinusoidally, because the crystal structure is moving around, it is vibrating. Velocity distribution you can see here. Now, mean square displacement here is increasing, but it is becoming almost it is not linearly increasing, but it will become constant after a certain time. So, because it is still crystalline structure. Now, if we change the boundary conditions, so let us make it periodic, because we want to look at periodic. Immediately the system relaxed. So, you can see that all the restrictions were gone, is now increasing in the step. Now, remember we are doing the time averaging. So, let us look at pause. So, average values, these are the time average. We have gone up to 1231 time steps, which is 2.6 10 to the power minus 9 seconds. Temperature is same 11.76 kelvins. Kinetic energy is 1.634 joules, and then potential is minus 4.788 joules, and number density is 3.41. Volume is 5.94 meter cube, and this is the pressure, which is 696 Pascal. So, if you look at here, this is the growth here happening because of periodic system. Now, if you look at it, is growing to grow, and what you want to watch out, average square displacement, that whether it is a liquid phase or the solid phase. So, now we are looking at the time average of the properties. We stop here, and let us say if we increase the temperature in order to break the system. Now, you will see trajectories, and let us look at atoms, and I am going to look at concentrations now, because velocity distribution has grown quite a bit, and energy versus time. Again, you can see the summation is constant, number density is constant, velocity distribution is constant around the central value. Then we go to pressure, which is now fluctuating and becoming gaseous, because now you can see there are some local order and disorder. These are the average properties that you are looking at. So, let me stop it. This is how we are doing time average. So, we are temperature, average temperature, kinetic energy, potential energy, and we do not have a bath. So, temperature is falling off a little bit, moving around, kinetic energy is here, potential energy is, and the volume is constant, and we can now see different situations. So, if we now change boundary condition, then we will see that we will be able to now create different situation and calculate the properties that we have been looking at. So, let us do the heat bath. So, that becomes canonical ensemble, and then in that new canonical ensemble you will see the averages of the properties, real units. So, let me now summarize understanding all these different parameters that we looked at in the molecular dynamics simulation, which we have been looking at in VMDL lab. We are able to look at the time trajectories, create the average of the properties, pressure, temperature, volume, energies, kinetic energy, potential energy, and also sometimes mean square displacement. So, looking at all these ideas, what we are understanding is that these are the basic properties that we can calculate. But now with these properties we can calculate some advanced properties of the bulk if we do periodic boundary condition, like specific heat, like diffusion constant. We can also then look at dynamic properties and structural properties. Structural properties could be, we are looking at the mean square the velocity autocorrelation function, which is the dynamic. Structural property will be g of r, which is the radial distribution function. which will tell us how the particles are. Now, if you look at the dynamic property, how molecules are moving in mean square displacement, or velocity autocorrelation, what is the vibration they are having around their local position. So, now we have a very unique situation that we can go from solid, liquid, gas phase and look at all these properties. So, we can find out the specific heat in the solid phase, specific heat in the gaseous phase, specific heat in the liquid phase. We can also observe phase transitions of different kind, first order phase transitions. And then we can also look at some of the transitions due to pressure, because if you have Parnello-Rahman conditions with constant temperature, constant pressure ensemble, then we can have a calculation of the structural properties like elastic constant. One simple idea, and now we have so many applications. So, what we will do in the next section, we will now focus on each property and see what does it really mean and how we can calculate them. Thank you.